So, you've probably played around with ChatGPT, or maybe one of the other incredible AI tools out there. And if you have, you've used what's called a GPT. But what does that actually mean? Today, we're going to pull back the curtain and really dig into the tech that's powering this whole revolution. And we're going to focus on that one crucial letter, the T. All right, let's get into it. First things first, what do those three letters even stand for? You might know the first two, but believe me, that third one, that's where all the magic is really happening. The G, well, that's for generative. This one's pretty easy to wrap your head around. The model generates or creates new original text. Simple enough. Then you've got P for pre-trained. All this means is that the model has already done its homework. It went through this massive learning phase where it basically read a huge chunk of the internet to learn all the patterns of human language. And finally, the T. This stands for transformer, and this is the key. This is the whole show. The transformer isn't just another part of the system, it's the core invention, the architectural breakthrough that kicked off this entire AI boom. And that is what we're going to break down today. So here's the central puzzle, the thing that feels almost impossible. At its very heart, a GPT model is just trying to do one simple thing: predict the most likely next word in a sentence. That's it. So how does a task that simple lead to it writing entire essays, poems, or even lines of code? It feels like it shouldn't work, but it absolutely does. And to understand how, we have to follow the data on its journey. Okay, so the first step is basically translation. See, a computer can't understand the word cat or house. It only gets numbers. So we've got to convert our language into its language. And the way we do this is actually surprisingly cool. This process is called word embedding. Every single word, or what the system calls a token, gets mapped to a totally unique vector. And a vector is just a fancy name for a long, long list of numbers. And I mean long. For GPT-3, we're talking a list of over 12,000 numbers for just one token. But these aren't random numbers. They're very carefully chosen to capture the actual meaning, the very essence of that word. So try to picture these vectors as coordinates. They're like coordinates for every word in this huge, multi-dimensional space. And what's so amazing is that in this space, the relationships between words become geometric. The distance and the direction between words actually starts to mean something. So words that have similar meanings end up clustering together. This is where it gets really mind-bending. Check this out. If you take the vector for the word king and you subtract the vector for man, and then you add the vector for woman, the result you get is incredibly close to the vector for queen. Think about that. The model hasn't just memorized definitions. It has learned a direction in this invisible space that literally represents the concept of gender. It's wild. And it's not just for abstract ideas like that. The model learns cultural relationships just from reading all that data. Get this. In some models, if you do the math for sushi minus Japan plus Germany, you get bratwurst. It has figured out this connection between a food and its country of origin all on its own. Okay, so we've got our words turned into these meaningful numbers. But, a word's meaning can change completely depending on the context, right? So let's jump into the next part and see how the transformer, the T, actually handles all of that. So here's a quick roadmap of the journey. Our vectors, fresh from that embedding step, now start flowing through a series of processing blocks. The two big ones to know are the attention block and the feed-forward block. And this cycle just repeats over and over and over again. So what do these blocks actually do? Well, you can think of the attention block as the place where the vectors get to look around and talk to each other. They figure out which other words in the sentence are important for understanding their own meaning. Then, the vector moves to the feed-forward block, sometimes called a multi-layer perceptron, which processes each vector one by one. It's almost like it's asking each vector thousands of tiny yes or no questions to really sharpen and refine its meaning. So the whole point of this entire complex dance is to do one thing, to transform a vector that just means king into a vector that means a Scottish king who murdered his way to the throne as described in Shakespearean English. It's all about letting that vector soak up all the rich, specific context from everything around it. All right, so our vectors are now packed, just brimming with all this rich contextual meaning. But there's still just a list of numbers. So the final step is to turn that super refined vector back into a word that you and I can actually read. And this is where a really clever mathematical tool called the softmax function comes into play. It takes that final, context-heavy vector and uses it to generate a score for every single possible word in its vocabulary.
Then, softmax does what its name implies. It squashes all those scores down into a clean probability distribution, where every word gets a percentage, a chance of being the very next word. And we can actually control how the model chooses from all those probabilities. There's a setting called temperature. If you set the temperature low, the model plays it safe. It's predictable, always picking the most likely word. But if you crank the temperature up, you're encouraging it to take risks, to give some of those less likely words a shot. And that can lead to way more creativity, or, sometimes just complete gibberish. So we've seen all the individual pieces now, right? We've gone from words to numbers, we've added a ton of context, and we've turned those numbers back into word probabilities. Now it's time to connect it all and finally solve that mystery we started with.
The real magic isn't in any one single step. It's in a simple, relentless loop. The model predicts the probabilities for the next word, it picks one, and then, and this is the absolute key, it sticks that new word onto the end of the input text and starts the entire process over again. And that right there, that's the aha moment. It's this simple act of predicting, then sampling, then adding, and then repeating that transforms a simple next word predictor into this powerhouse of a generative engine. All the complexity and coherence we see just emerges from thousands and thousands of repetitions of this one tiny task. But you might be wondering, how can a loop that simple be so powerful? Well, it's because it's being powered by a model of just absolutely immense scale. This number, that's 175 billion. That's how many tunable parameters or weights are inside of GPT-3. You can think of these as the brains of the operation, all the intelligence it gained from that pre-training. The simplicity of the loop only works because of the incredible complexity of the model that's running it. So, the T in GPT, the transformer, is what makes it all possible. It's an architecture that lets a very simple predictive loop produce these unbelievably complex results, and it all starts by turning our language into geometry. If this much power can be unlocked from such a simple core idea, it really makes you wonder, doesn't it? What new puzzles is AI going to solve next?